So what about noise? We use Nyquist pulses to help us avoid intersymbol interference. Some pulses use more bandwidth than others, and bandwidth may simply not be available. We may want to create a more spectrally efficient, densely packed wavelength AWGN system, for instance. Practical concerns can lead to ISI even if we are using a Nyquist pulse. So Nyquist pulse doesn't absolutely assure you of ISI, it just helps you. And remember that BER as a function of SNR does not include any ISI effects, but it is something that we can deal with analytically. So if we want to take into effect, for instance, ISI effects, we would have to look to a numerical simulator because it's just not tractable analytically. To close up this topic, talk a little bit about how you go about simulating a sampled additive white Gaussian noise. Additive white Gaussian noise is a random process. N of k is a sample of one of the, at an instant of time of that random process. It is a random variable. This random variable has a Gaussian distribution, it's zero mean, and it has a variance of sigma squared, which we write as I showed you before. So if we consider a random process N of t, which has a typical form that we see here, we'll see on an oscilloscope. When I sample it in my receiver at specific times, these become random variables, each of which is independent of the other, and each of which has a Gaussian, the same Gaussian distribution. So we call that IID, independent and identically distributed random variables. You can show that these are indeed independent, and because of that independence, the autocorrelation function follows directly as being a delta function, and in the frequency domain as being flat in the frequency domain. And that follows directly from the independence. So what happens? So now we know the autocorrelation function and the power spectral density of additive white Gaussian noise, which has infinite frequency response. So what happens when we filter it? Suppose we filter it with an ideal low-pass filter, for instance. If we filter it with a low-pass filter, well, now the power spectral density is a rectangle instead of being flat over all frequencies, and this means that we create colored noise, which means that the noise samples are not necessarily independent from one another, which complicates any simulation greatly. However, it doesn't really, because if we use Nyquist pulses, then we know that at the sampling times, which are when we're interested in the statistics of the samples of the noise, so if we sample at regularly at the bit rate, and these are a Nyquist filter, not necessarily an ideal Nyquist filter, but any Nyquist filter, that indeed the samples will not be correlated, and uncorrelated noise samples which have Gaussian distribution are also independent noise samples. So that means that when we go into the simulator, we can simulate the noise samples as being independent from one another.